I wanted to go over my notebook from today's meet session just in case you weren't able to be there. It covered a lot of the big ideas of AP statistics. So in case you haven't mastered the concepts yet, hopefully within the next 24 hours, you become an expert in statistics. All right, let's go. So categorical versus quantitative. This is the question you need to start out asking yourself. When you read through these questions, you need to know what you're working with. What kind of data is it? Categorical, we're going to be using P's if we're looking at the population proportion, or P hat if we're working with sample proportions. But it really comes down to this idea is can you put things into categories? Can you think of something as a success or a failure? Binomial probability is also categorical because we break it down in the same idea, success or failure. With quantitative data, we're going to hear words like average or mean, and there's going to be a measurement. If there's a unit attached to the numerical value, then you're working with quantitative. So again, we're going to see things like mu, or we're going to see X bar. These are quantitative notations. All right, you're probably going to be asked about checks and assumptions. Now, regardless of whether you're working with categorical or quantitative data, you're looking for three things in order to run a significance test or construct a confidence interval. You need to have a random sample, or if you're looking at an experiment, random assignment of the treatments. You also need independence. This is independence between the trials. So you could have two things. One, they might just say that it's sampled with replacement. That guarantees independence if you're sampling with replacement. I promise that's what that said. Replacement. Or without replacement would mean you should probably check that N isn't too large, that it's less than 10% of the entire population. Because if that's the case, then you can go ahead and proceed, and capital N means population, by the way. That's the notation. Okay, you can go ahead and proceed because your sample size is such a smaller fraction of the entire population that you're still going to get independence between trials, as long as you're conducting a random sample. And then we come to normality. And normality changes based on whether or not you're working with categorical or working with quantitative. So regardless of which one you're working with, you're going to want to see, is my sample large enough? So analyzing if your sample is large enough with categorical means, do you have at least 10 successes and at least 10 failures? Now, the calculations will need to be shown for this. Is n times p greater than or equal to 10, and n times 1 minus p also greater than or equal to 10? And if you have more than one sample, you have to do this with each sample. Each sample has to have at least 10 successes and at least 10 failures in order for your sampling distribution to be approximately normal. Then we look at quantitative here. Quantitative, there are options. Okay? You still need to have a certain sample size, right, in order to use the central limit theorem. Central limit theorem is based off the idea that you have a large enough sample to guarantee the sampling distribution will be approximately normal. But what we've examined in class is that there are other ways to have a sampling distribution that's approximately normal. One is if the population is normal. Population's normal, then your sampling distribution is automatically approximately normal. Or the third way, you don't have a large sample size, however, you look at the sample data, you can see in the sample data that you don't have any outliers and it's not heavily skewed, meaning it's fairly symmetric, then you can still proceed and say that your sampling distribution is approximately normal. Now, I've said this about 10 times now. You need to say that it's approximately normal, right? That word is really important. Okay, so as long as these three are met, you can proceed with your inference procedures. All right, with that, let me talk about why we have to check with both samples and when we use P and when we use P hat. Okay, so let me go over what's written here and why it's written here. In a hypothesis test, we make this claim that P1 is equal to P2 or P1 minus P2 equals 0. Okay. Normally, with a significance test with one sample, we would just use n times P to show that it's greater than or equal to 10, or n times 1 minus P, because we would have been given this P value. Well, in a two-sample significance test, we don't know either one of these values. We just know that their difference is 0. Okay, so this is why on a two-sample significance test, your checks are actually that n1 times the sample P hat of from your first sample, your sample proportion is greater than or equal to 10, and n1 times 1 minus P hat from your first sample is greater than or equal to 10. Sorry, that should be a 10. And then we also have to check that n2, your second sample size, times your second sample proportion is greater than or equal to 10, and that 1 minus P hat of your second sample is greater than or equal to 10. Okay, this has to be checked with both samples. And the other thing, you have to say that these two samples are independent of each other. Okay, all right, let's keep rolling. So now let's look at notation. Notation, notation, notation. This goes back to, are you working with categorical or are you working with quantitative? Sorry, some of this stuff is hard to read. This is from our Google Meet earlier today. So population, you're working with parameters. You get P if you're working with categorical. This is the population proportion. You're working with quantitative, then you're going to use mu. That is the population mean. Next, we might just have sample data. That's called a statistic. So if we're working with categorical, our statistic would be P hat, and we'd also be given some sample size, that's n here, or if we're working with quantitative, our sample mean would be x bar. We're still going to be given sample size. And then lastly, if we take samples over and over and over again from the population, so I go from here to here multiple times, get lots and lots and lots of samples, and I put all those samples together, what I get is called a sampling distribution. Okay, so if I do repeated sampling of the exact same size, size n, and get P hat after P hat after P hat, and I put all those P hats together, what I get is called the sampling distribution. Now what we've learned is that the mean of the sampling distribution should be equal to the population proportion. It is an unbiased estimate of the population proportion, as long as you've sampled correctly. You've done a random sample and you've eliminated bias, okay? And then with quantitative, the notation becomes the mean of x bar. So you take sample after sample and you find the average. X bar, another X bar, another X bar, another X bar, and you put all those together, you get the mean of your sampling distribution, which is going to be the mean of the population, and your standard deviations right here. Remember, your standard deviation formulas are on your formula sheet, which brings me to my next slide. Let's talk about standard deviation. Okay, standard deviation, we're going to focus in on quantitative here. So when we look at standard deviation, this is from the population, we get sigma. Okay. Now, most of the time, we don't know sigma. So we have to calculate standard deviation from our sample. And then we use that to find the standard deviation of our sampling distribution. Sampling distribution is sigma of x bar, that's the notation. And you've got two formulas. You've got sigma over the square root of n, which is great, but most of the time we don't know sigma. So we have to do s, which is called the standard error over the square root of n. Now this brings me to why we have the t-distribution, okay? There are two parameters with quantitative. We have the mean of the population and we have the standard deviation of the population, okay? If we don't know these things, then we have to estimate them using x bar and using s, two statistics. So because of that, we get what's called the t-distribution. That says t-distribution. So let's look at the normal curve. We're typically looking at a normal curve, approximately normal. What we've learned is that you're within your mean. If you go out one standard deviation in both directions, that's going to be 68% of our data. Without out two, that's about 95%. Out three, that's about 99.7%. Okay, that's the empirical rule. It's a generalization. The t-distribution is saying, wait a minute, we are estimating two parameters. We're not only estimating the population mean by using x bar, we're also now estimating the population standard deviation by using S, our sample standard deviation. We're going to need to allow for sampling error. Remember, sampling error is also called natural variability. It happens. I use that word error. That doesn't mean we did anything wrong. So what the t-distribution is, it says, okay, we're going to allow for a little bit more variation in the tails. The distribution won't peak so high. And it allows just for a little bit more variation. And it's based on what's called the degrees of freedom, which is n-1. Now, one of the biggest concepts associated with this is that this t-distribution you see in blue will become more and more normal. So the blue curve here will start to look more like the black curve here when you increase n. As you increase your sample size, you will decrease variability, which means your t-distribution, as n approaches infinity, basically becomes the normal curve, okay? And what do I mean by variability? I mean standard deviation, okay? Look at the formula. Look at this formula right here. S divided by the square root of n. So as my sample size increases, this entire calculation here is going to get smaller and smaller and smaller because n is in the denominator. That is going back to fundamentals of math. All right. So as n increases, your variability, your spread decreases.